Hey everybody, it's Wednesday, November 4th. As you can see here from the aim today, our main focus for this video is going to be to cover the first of many problems that we are going to look at where we are going to apply Newton's laws to analyze the motion of systems. And so if you remember in yesterday's video, at the end, after we wrapped up all three of Newton's laws, we began to talk about free body diagrams. And now basically our main focus for the next week and a half is going to be to discuss how we can apply free body diagrams to a bunch of different systems in order to solve problems. And so today we will begin that by taking a look at a classic physics problem called the elevator problem, which deals with objects moving inside of elevators, or really I should probably say objects inside of elevators which are moving. So the first thing I want you to write is the elevator problem is a classic physics problem in which we attempt to determine how the scale reading of the scale that the person is standing on inside of this elevator changes based on the motion of the elevator. And so that's what we're looking at here. In these elevator problems, we have an elevator, and inside of that elevator, we have a person standing in that elevator on top of just like a traditional bathroom scale. And essentially what our task here is to figure out how the reading on the scale is going to change based on the motion of the elevator. And the way that we're going to analyze these situations is by making use of these free body diagrams that we developed yesterday. Take a second to pause this video here and write that down, and when you hit play, we'll move on. So the first thing we should do here is we should ask some questions. The first question we should ask is, what does a scale measure? It's not so obvious. I would say that most people would answer, a scale measures an object's weight. But that's actually not true. While it seems like a scale measures a person's weight, the scale is actually measuring how much it is pushing up on the person to support their weight. So really the big question we have to ask here is, well, what does that mean? The scale is not actually directly measuring a person's weight. The scale is measuring how much it's pushing up on the person to support their weight. And what that means is that the scale reading in an elevator problem measures the normal force acting on a person. Now, because you've probably, I'm just going to go ahead and take a guess, because you've probably never weighed yourself inside of an elevator, every time you've ever stepped on a scale, it's been in a stationary room and the scale itself is stationary. And so essentially by measuring the normal force, the scale was indirectly measuring your weight. As we said yesterday and Monday, when you're on a flat horizontal surface, the normal force is equal to the weight. But now because this flat horizontal surface and these elevator problems are going to be accelerating, we have a different story. So the key idea here is that the scale reading in an elevator problem measures the normal force acting on a person. Take a second to pause this video here and write that down, and when you hit play, we'll move on. So this is an important point here before we move on, because it's critical that everybody understands this. Even though we say that gravity is the force that gives us the sensation of weight, it's just gravity that pushes our valence electrons closer to the valence electrons on the surface, which gives rise to the normal force. And so the reason that we are able to sense our weight is the fact that the surface upon which we are standing exerts a force on us. Now, why am I bringing this up? Because in physics, and this is actually not really true in general, but it's just true for this topic, when it comes to talking about weight, we get very careless with language. And the way we get very careless with language in these situations is essentially by using the word weightless. Because we say, like, well, when an object is in orbit, it's weightless. That's why you see astronauts in orbit floating. But I think that's a bad way to describe it, because when you say weightless, it kind of makes it seem like the person has no weight, which means no force of gravity, but that's wrong. And so I want to just be very clear about this, that when we say someone is weightless, essentially what we're saying is that the normal force acting on them is zero. They still have a force of gravity acting on them, and so they still have a weight, because weight is the measurement of the force of gravity, but the normal force acting on them is zero. Because they're not being pushed into a surface, there is no surface pushing back on them, and so they are not able to sense their weight, because the way we sense our weight is through the normal force, which really is how a scale senses weight. This is a very important idea that's going to come up quite a bit this year. So take a second to pause this video and write that down. And when you hit play, we'll get more into specific details about the elevator problem. So before we move on, we should just say, because the normal force is how we sense our weight, or in other words, that's how our weight appears to us to feel. Another way of asking about the normal force is by asking about the apparent weight, or the scale reading. In a lot of cases, they will simply ask you for the scale reading, but other times they'll use the phrases like apparent weight. And when they're talking about apparent weight, what they're talking about is the normal force. So when we get into the specific details for the elevator problem here, essentially what we're going to do is we're going to break all elevator problems into three categories. And we're going to say here there are three cases of motion that we want to deal with when we're talking about an elevator problem. The first case is when the elevator experiences an upward acceleration. Notice here, we are simply talking about the direction of the acceleration vector, not necessarily how the elevator itself is moving, but just the direction of the vector. So when the acceleration vector is upward, that falls under case one. Case two is when the elevator experiences downward acceleration. And case three is when the elevator experiences no acceleration. Take a second to pause this video and write that down, and when you hit play, we'll jump into case one. When you're analyzing a situation where you have an object that's moving, you have to sort of take the clues that the problem is giving you in order to be able to answer the question. So the first big question we have to answer here is, if the elevator has an acceleration which is upward, like, what is the first big piece of information that you can get from that? If the elevator is accelerating upward, what does that tell you immediately? And what I hope you realize is that whenever, and this is not just true for this problem, it's true for all problems, whenever you are told the direction of an object's acceleration, then you are also technically being told about the net force. And so what we can say here is that since the acceleration is upward, F net is upward. Why? Because the acceleration, according to Newton's second law, is directly proportional to the net force. So since the acceleration is upward, the net force is upward. And that gives you some really good info, because it allows you to determine the relative size of forces that are acting on the person in the elevator. And we'll talk about what that means here in a moment, but let's at least say first, we've got to figure out what forces are acting on the person if we are going to figure out the relative size of them. So the first thing we should say is the object interacts with a few other objects, and we want to figure out what those are. So if a person is standing in an elevator, what are they interacting with? Well, obviously we have the person-earth interaction, and because the person is standing on the scale, we have the person-scale interaction. And so we should ask the question, well, then how many forces should be drawn in our free body diagram? And I hope everybody realizes that it's 2, because there are 2 interactions happening here with this person. The person-earth interaction is going to give rise to the gravitational force. The person-scale interaction is going to give rise to the normal force. And so our free body diagram should include those 2 forces. And so I'm going to draw my dot showing the center of the person, and off to the side, I'm going to draw the acceleration acting upward. And so my free body diagram is going to have 2 forces. It's going to have a normal force acting up, and it's going to have a gravitational force acting down. But now here's the big question. How big are we supposed to draw the gravitational force compared to how big we drew the normal force, based on the information given here about the motion of this object? Well, based on the motion of this object here, we know that if the person has an upward acceleration, the F net is upward. And the only way the net force can be upward is if the upward force is bigger than the downward force. And so that means that we have to draw the FG as being lower. And so let's write here in parentheses as a little note, Fn, the normal force, is greater than Fg for this case of upward acceleration. And now the last thing we want to do before we move on is go ahead and write the equation based on that free body diagram. And as we said yesterday, when you are writing an equation from a free body diagram, you take MA and you set it equal to the forces going in the direction of the acceleration minus the forces going in the opposite direction. And so we have the force going in the direction of the acceleration, the normal force, and then we subtract the forces going in the opposite direction, which in this case is just Fg. Now I'm going to rewrite this equation as Ma equals Fn minus mg, because the weight of an object is equal to m times g. And at this point, it would be very important for everybody to resist an urge. I'm sure some of you have, because almost all of the time so far that we spent thinking about the normal force, what we've always said about the normal force is the normal force is equal to the weight. But the point that we're trying to make here is the normal force is not equal to the weight. The normal force is bigger than the weight, as we said down here underneath the free body diagram. And so the important thing to remember is that here, in almost all these elevator problems, your goal is to solve for the normal force. And as you'll see here, it's not equal to the weight. Notice if we go ahead and we solve this for the normal force, we get the normal force, Fn, is equal to Ma. And then when we add the mg over to the other side, we get plus mg. And I could squeeze this down here, but I'm just going to write this over to the side because I've got room over there. Notice, because both of those terms have a mass, we can factor it out. And so what we get when we fully solve this for the normal force is that the normal force is equal to the mass times A plus G. And so what that tells us is when the acceleration gets bigger and bigger and bigger, the normal force or the scale reading is going to get bigger and bigger and bigger. And I think that actually makes sense if you really think about it, because if this person is accelerating upward, essentially what the bottom of the scale is doing is it's pushing up on the person. And essentially all we're really saying is that when the person is accelerating upward more, the floor is pushing upward more on the person's feet. I think that makes pretty good sense. So here we have the normal force is equal to m times the sum of A plus G. Now, the way we determined what the free body diagram looked like, based on the information given about the acceleration, is like really one of the more important points here for this problem. And so I want to take a second to sort of summarize that thinking before we move on to the next case. The first thing we should say here is for a single object inside the elevator, like the person, there are only two forces acting on the object. And I think sometimes people get bogged down in the details when they're looking at these problems. This is really simpler than it might look, even when they try to make it complicated. When you're given the acceleration, you can use the acceleration to determine the direction of the net force, which gives you information about the relative size of the forces. In other words, which one is larger. If you know the acceleration is up, then you know the net force is up. And if the net force is up, the upward force has to be bigger than the downward force. The converse is true. If the acceleration is down, then the net force is down, which means the downward force has to be bigger than the upward force, because if the downward force wasn't bigger than the upward force, then the net force wouldn't be down. That's the idea. So when you're given the acceleration, you can use the acceleration to determine the direction of the net force, which gives you information about the relative size of the forces. The opposite is true then also. When given the relative size of the two forces, so if they don't tell you the direction of the acceleration, but they just tell you how big each force is, you can use that information to determine the direction of the net force, because the net force is going to be in the direction of the bigger force, which gives you information about the direction of the acceleration. So if the upward force is bigger than the downward force, then you say, well, the F net is up. And if the F net is up, then the acceleration is up. And that really is what your explanations are going to look like, by the way. If I tell you a person who weighs 600 newtons is standing on a scale, and the scale says 610 newtons, then the fact that the scale reading, which is the normal force, is bigger means the net force is upward. And if the net force is upward, the acceleration is upward. These are pretty basic ideas that we're talking about. There are two forces. When they're opposite, you add with the signs. You do some basic thinking about that, and you realize the net force has got to be in the direction of the bigger force. And since the F net is directly proportional to the acceleration, whatever direction the net force is in, well, that's the direction of the acceleration. Take a minute to pause this video here and write that down. And when you hit play, we'll move on to the next case. Okay, moving on to case 2. Case 2, as I'm sure you realize by now, is going to be basically just the opposite of what we saw. Either way, we should take a second to just go through it here. And so the first thing we're going to say is that when this thing is accelerating downward, our note here is going to say, since the acceleration is downward, F net is downward. Why? Because the acceleration is directly proportional to F net. And, of course, just like we had last time, we have two interactions. We have the person-Earth interaction, and we have the person-scale interaction. And so our free body diagram is going to look somewhat similar, right? Because it's going to have two forces. Those two forces are going to go in opposite directions. But as we just established in that last note, the direction of the acceleration determines the relative size of the two forces. And so in this particular situation, we have the normal force going up, and we have the gravitational force going down, or the weight going down. But now, since the net force is downward, the weight has to be bigger than the normal force. And so we'll draw our arrow for the weight, Fg, going down, and we're going to make the normal force arrow smaller than that. And we'll just write here off to the side, just as a little note, in this case, the normal force is less than the weight. And the normal force is less than the weight because it has to be in order for the Fnet to be down. To be clear, you don't have to write this every time. This is just a note for you guys because this is the first time we're looking at this. And now that we have our free body diagram, we can write the equation from our free body diagram. And so, as is always the case with free body diagrams, we take ma and we set it equal to the forces going in the direction of the acceleration. In this case, that's Fg. And then we subtract the forces going opposite the direction of the acceleration, which is the normal force. Once again, I'm going to rewrite this to plug in mg for Fg, the weight. And so I have mg then minus Fn. And the whole point of this is to solve for the scale reading, so I'm going to go ahead and solve for the normal force. And I'm going to do that by adding the normal force over to the other side, and then plugging in the numbers here, I have mg minus ma. And just like we did before, the normal force here has an equation with mass in both of the terms, and so I can factor that out. So I have Fn equals m times g minus a. So first of all, it should be pretty easy to see the pattern that emerges here with these equations. Notice this one for the normal force, the equation for the normal force is m times g minus a. And for upward acceleration, we have the normal force is m times g plus a. And it's easy to see why those equations make the normal force either larger or smaller than the weight. Because the weight is mg. And in this case, we're adding something to g and then multiplying it by the mass, which of course is going to make the normal force bigger. And just the opposite over here, because the weight is equal to mg, and now before we actually do the calculation, we subtract a from g before we multiply it by the mass, then we're going to get a normal force that's smaller. So that's it for case 2. We've got our equation, we've got our free body diagram. Now we'll go to probably the easiest case of all, which is the case of zero acceleration, case 3. And so what we'll write here, again, same sort of format as the other slides, our note here will be, since the acceleration is 0, and this I want you to think about here, since the acceleration is 0, what can we say about the net force? Of course, since the acceleration is 0, Fnet is 0. Why? Because A is directly proportional to Fnet. And just like we had last time, and the time before that, this is always the case when there's just a person standing on a scale in an elevator, the interactions we have are the person-Earth interaction, and we have the person-scale interaction. And as we said in the slide that we showed before the last one, the information about the acceleration can give you information about the net force, which gives you information about the relative size of the forces. So when the acceleration is up, the net force is up, which means the upward force is bigger than the downward force. And as we just said, when the acceleration is down, the net force is down. And so that means the downward force is bigger than the upward force. But when the acceleration is 0, the net force is 0, which means the two forces cancel each other out. And so here, our diagram is going to show these two forces as the same size. And so we try to draw these arrows with the same length because they're equal. The normal force is equal to the weight. And so as we mentioned, the diagram showing these two vectors as being roughly the same size, maybe this one should be a little longer, shows us that these two things are equal. Now, when it comes to writing the equation, We said the other day that when you're writing an equation and you don't know the acceleration's direction, you can just like pick a direction. And so we'll write the equation assuming the acceleration is up. And so if the acceleration is up, we can say, well, we take the forces in the direction of the acceleration, the normal force, minus the forces opposite the direction, which in this case is Fg. But it doesn't really matter which direction you assume, because either way, when you acknowledge that the acceleration is zero, thus making the whole ma term go to zero, what you end up with is just that these two forces are equal. And that's it. So here, we show that these two forces are equal when the elevator is not accelerating. And that could be when the elevator is at rest or moving with a constant speed. And that's an important thing to recognize here. Okay, so now we can see how this works when we're solving problems. And before we do that, here's a little summary of what the free body diagrams look like for all of these situations that we just looked at here. So notice for constant velocity, we see that the normal force and the weight are equal. And so we can include these here because they only showed them on the side. When it's accelerating upward, the normal force is bigger than the weight. That's because the F net has to be upward. And when it's accelerating downward, the weight is bigger than the normal force. A very important reminder before we go ahead and solve a problem is, since the free body diagram takes care of all of the directions for us, we only need to use the magnitudes of all accelerations in elevator problems. The diagram is showing us the direction, so we don't need the sign of the acceleration to do that for us, because the diagram is going to do it for us here. Take a second to pause this video here and write that down, and when you hit play, we'll go ahead and take a look at a good sample problem. So this is a good sample problem for the elevator. It says here in this example, it takes the elevator in a skyscraper 10 seconds to reach its cruising speed of 20 meters per second and 5 seconds to slow to rest from its cruising speed. A passenger with a mass of 75 kilograms gets aboard on the 40th floor with plans to go toward the second floor. What is the apparent weight of the passenger? A, before the elevator starts moving. B, while the elevator is speeding up, leaving the 40th floor. C, while the elevator is at cruising speed. And D, while the elevator is slowing down to arrive at the second floor. Okay, we're going to take this part by part. Part A is asking us what is the apparent weight of the passenger before the elevator starts moving. The first thing we want to note here, for sure, is that the question is asking us what is the apparent weight of the passenger. And that when they ask us for apparent weight, essentially what they're saying is, what does the scale tell the person they weigh? Or in other words, they're asking us for the normal force. So for part A, before the elevator begins moving, we have a pretty simple task here. And what I want everybody to realize is that despite the fact that you may know the answer here, and every time you get these on the homework, you can always just go and look at your notes and look up the equation, it's critical that every time you solve these problems, you do it from scratch by writing the free body diagram, or drawing the free body diagram by writing the equation from the free body diagram, and then go ahead and solve it. Because the AP test is never just going to ask you a calculation problem where they tell you, this is the acceleration, this is the mass, figure out the normal force. They're going to say, draw the free body diagram and then derive the equation. They're actually probably never even going to tell you to plug in the numbers. And that's an important thing to realize. And so for part A here, before the elevator starts moving, we should note here that the acceleration in this instance is 0 meters per second squared. G, of course, is 9.8 meters per second squared. The mass of this passenger, as they told us in the problem, is 75 kilograms, and we're being asked for the normal force. Because the person is not accelerating in this elevator, because the elevator is sitting there at rest, the normal force and the gravitational force are the same size. And so here we can say the sum of the forces is going to be equal to 0. And so that means the normal force, the upward force, minus the gravitational force is going to equal 0. And so what that tells us is the normal force, as we know from the example that we just did, is equal to the weight. And that, of course, means the normal force is equal to m times g. And so plugging in here, we have the mass, 75 kilograms, times g, 9.8 meters per second squared. And when you do that math, 75 times 9.8, taking into account the units, you get 735 newtons. So that's the weight of the person, 735 newtons. And that's the normal force before the elevator begins moving. And this diagram, notice, this is something I always think is important to check before you move on. It's easy on the AP test because they give you that grid space, but you really want to make sure if you intend for these to be the same length, that you show them as being the same length. Now, it's easy if you're doing it on a piece of paper because you can just use a ruler to make sure the lines are straight too. I can't really do that with this digital pad here, but you get the idea. And so that's that. Now, for B says, what is the apparent weight of the passenger while the elevator is speeding up, leaving the 40th floor? Now, this is the part that's a little tricky. For part B, I'd like everybody to first, because you obviously need to do this first, I'd like everybody first to solve for the acceleration of the elevator using regular old-fashioned kinematic equations. Using regular old-fashioned kinematic equations, what is the acceleration of the elevator? Go ahead and pause this video here and solve for the acceleration, and when you hit play, we'll go over it. So the important thing to realize here is that the elevator is starting on the 40th floor, and it's going down toward the second floor. And so here, for part B, we have the initial velocity of the elevator being 0 meters per second. The final velocity here is negative 20 meters per second because the elevator is going down. And so the final velocity should be negative. And they tell us in the problem that takes 10 seconds. We're looking for the acceleration. So the acceleration here is going to be final velocity minus initial velocity over the time. And that's going to give us negative 20 meters per second minus 0 meters per second. And that's over 10 seconds. And so we get here negative 20 over 10, and that's going to be negative 2 meters per second squared. Now, it's important to realize while this seems like it contradicts the note I just put up before we looked at this problem, it doesn't. Because when we use the free body diagram equation, we are going to just use 2 meters per second squared. But it is critical before we do that we definitively establish here that the elevator's acceleration in this instance is down, because that transforms everything that we need to do for this problem. And so here we have G is equal to 9.8 meters per second squared. We have A equal to 2 meters per second squared. And we know that the mass of this person is 75 kilograms. And we're looking for the normal force. So in our free body diagram, since we know the elevator is accelerating down now, when we draw our diagram, we're going to show the weight acting down, and we're going to show the normal force acting up, but the normal force is going to be less. The normal force is going to be less than the weight because the acceleration is down, meaning the net force is down. So I can also show this on the side here. Remember, you do not want to connect that acceleration vector to the dot in the diagram. That needs to be off to the side. And so when we write our equation, we take ma and we set it equal to the force going in the direction of the acceleration, Fg, minus the force going in the opposite direction, Fn. And I'm going to do this in one shot here. Now I'm going to solve for Fn, and I'm going to substitute in mg for Fg. And so that gives me Fn equals mg minus ma. And so when I do that, I get Fn equals m times g minus a. Notice here, remember, I said we are not going to use the sign because the fact that the acceleration is negative is already taken care of by this negative sign. And so I'm just going to plug in the magnitude of 2. And so I have Fn equals the mass, 75 kilograms, times 9.8 meters per second squared, minus 2.0 meters per second squared. And so essentially my normal force here is just going to be 75 times 7.8 meters per second squared, because I'm taking 9.8 meters per second squared and minusing 2, subtracting 2. So when you do that math, you get 585 newtons, which is 75 kilograms times 7.8 meters per second squared. So notice we already calculated here that the weight is 735 newtons. When the elevator is accelerating down, the normal force is less than the weight. Pretty good. Okay, moving on to part C. Part C says, what is the apparent weight of the passenger while the elevator is at cruising speed? You should already know this one, because we already solved for it. While the elevator is at cruising speed, the elevator is not accelerating. And if it's not accelerating, then the net force is 0. And that means the normal force is equal to the weight, which is the same as the answer for part A. So what we're going to do here is we're going to do this, and we're going to write A plus C. And this is our answer for part A and C. So we'll say, while the elevator is at rest or moving at a constant speed, Fn equals Fg, because Fnet is 0 newtons, because A equals 0 meters per second squared. And again, that's true because the net force and the acceleration are directly proportional. Take a second to pause this video here and write that down. And when you hit play, we'll go ahead and answer part D. So for part D says, what is the apparent weight of the passenger while the elevator is slowing down to arrive at the second floor? So what we're going to need to do is we're going to need to do something that's very similar to what we did for part B, because while the elevator is slowing down, it says here that there's a different amount of time it takes for it to slow down. And so we're going to need to figure out what the acceleration is and then use that to calculate the apparent weight. So our list of knowns should look very similar to our list of knowns for part B. So we'll write here part D, and we'll say the initial velocity is going to be that cruising speed of negative 20 meters per second. The final velocity is going to be 0 meters per second. The time now is 5.0 seconds. If you missed that, let me just go back. It says here that it takes 5 seconds to slow from rest from its cruising speed, slow to rest from its cruising speed. So we need to use that, obviously, when we're calculating the acceleration. And of course, we're looking for the acceleration, so that's our unknown here. So we have the acceleration is equal to the final velocity minus the initial velocity over the time. And so that means our acceleration is going to be 0 meters per second minus negative 20 meters per second over 5.0 seconds. And 0 minus negative 20 is positive 20, and 20 over 5 is going to be a positive 4 meters per second. Now, the reason why we want to establish that, of course, is because the direction of the acceleration really matters. And so I'm going to write here 4 meters per second squared up. So the acceleration is 4.0 meters per second squared. The acceleration in this case is up. And the fact that the acceleration is up here is everything we need to know. So we know that g is equal to 9.8 meters per second squared. We know here that our acceleration is 4.0 meters per second squared. We know that our mass for our person is 75 kilograms, and we're looking for the normal force. So we draw our free body diagram, and our free body diagram should be the free body diagram for an object that's accelerating up. So we have our normal force going up, and in this case, that's going to be bigger than the weight of the object, so I'll draw that arrow smaller. And like we always are going to do for free body diagrams, we take ma, and we set it equal to the force going in the direction of the acceleration, Fn, minus the force going in the opposite direction of the acceleration, which is Fg. And like I did last time, I'm going to go ahead and solve this for the normal force and plug in for Fg at the same time. So I get Fn, the normal force, is equal to ma plus mg. And of course now, because both of my terms have an m in it, I can factor it out. And of course, if you want to do that in that step also, feel free. And so we get Fn, the normal force, is equal to m times a plus g. And so our normal force here then is 75 kilograms times a, 4.0 meters per second squared, plus 9.8 meters per second squared. And so to solve this for the normal force, basically we're just taking 75 times 13.8 meters per second squared. And when you do that math, you get 1,035 newtons. We're not going to go nuts about sig figs for this problem. So as we see, when the elevator accelerates up, because the net force is up, the upward force, the normal force, has to be bigger than the gravitational force. And that's it for this problem. So before we wrap up the problem-solving portion for the elevator problem, let's just say two things, two little notes from that problem. The first note, of course, as we've said a bunch of times, is that scale reading, or apparent weight, is another way of asking for the normal force, because a scale actually measures the normal force. That's the force the scale puts on you. So that should be obvious by now based on what we said. Another important note, as you probably saw from that particular problem, is that when the initial velocity and the acceleration, when v naught and a are in the same direction, the object is speeding up, and when they're opposite, the object is slowing down. So sometimes they're just going to say the thing is accelerating upward with an acceleration of blah, blah, blah. But like in this one, they could also just say the elevator is going from blank floor to blank floor with this speed, and you'll need to figure out based on the motion of the elevator whether it's speeding up or slowing down. And so in the last problem, we saw that the elevator was speeding up in the beginning, but because it was going from a higher floor to a lower floor, it was speeding up in the direction it was moving, and so the acceleration was actually down because the elevator was moving down. Then, of course, the elevator was still going down, and when it slowed down, because the acceleration is in the opposite direction when an object slows down, the acceleration was actually directed upward. So that's an important thing to remember. Take a second to pause this video here, write that down, and when you hit play, we'll move on to the last part of this video. To finish up this video for today, the last thing we want to discuss very briefly is the other kind of elevator problem that you could see in this course. And that other kind of elevator problem that you could see in this course is an elevator explanation. So instead of solving the problem like we just did, you'll have to explain. And all elevator problem explanations should include the following elements. It should include an establishment of the direction of the acceleration, a discussion of the relationship between the direction of the net force and the acceleration, and a comparison of the size of the normal force, which can be described as either the scale reading or the apparent weight, to the actual weight, which is the size of the gravitational force. And depending on what information you're given in the problem, the order in which you address these things can change. If they automatically tell you the direction of the acceleration, you say, well, since the acceleration is, up or down, that means the net force is up or down, which means this force is bigger than that force or whatever. But of course, if they tell you the weight is this and the normal force is this, then you'll say the weight is bigger or smaller than the normal force. And since, whichever one is bigger, that means the net force is in that direction. And since the net force is in that direction, the acceleration is in that direction because they're directly proportional. So regardless of whichever order, so to speak, or whichever information you're given in the problem, those are the three things which should always be included in your answers. Take a second to pause this video and write this down, and then we'll go ahead and look at an example. Okay, so here's a good example of an elevator problem explanation. This example here says a 750 Newton person stands in an elevator that is accelerating downward. The upward force of the elevator floor on the person must be. And so the first thing we need to realize here is that when they say a blank Newton person, what they're telling you is Fg, the weight of the person. What they're asking you for here is the upward force of the elevator floor on the person. Essentially, what they're asking you about here is the force the surface exerts on the person. And that is the normal force. They also tell you that the elevator is accelerating downward. And so that information, the fact that the elevator is accelerating downward, is the information you should seize on first. So the first thing we would say in our explanation is, in this situation, the elevator is accelerating downward. Since the elevator's acceleration is downward, and the net force is directly proportional to the acceleration, the net force is also directed downward. Since the net force is directed downward, now notice what we've done here is we've established the direction of the acceleration, we've discussed the direction of the net force, now we just had to compare the forces. And if the net force is down, that means the downward force is bigger than the upward force. So what we're going to say here, since the net force is directed downward, the downward force of gravity, and I'm going to write in parentheses here the person's weight, must be larger than the upward normal force exerted by the floor of the elevator, which is going to be the scale reading or the apparent weight. And so if the downward force of gravity must be larger than the upward normal force, if the weight is 750 newtons, then that's going to make the answer choice 2, less than 750 newtons. Take a second to pause this video here and write down this explanation. And when you hit play, we'll take a look at one last example before we go. Okay, so for this last example before we go, I'd like you to try this one on your own and submit it. Here's the question. It says, based on the information given in the video, what can you say about the motion of the elevator? Be sure to follow the format for the elevator problem explanations in your answer. So let's take a look at the video. In this video here, we see a person standing on a scale in an elevator. The elevator has not yet started moving, and we can see what the reading on the scale is. And as soon as I hit play, the elevator is just about to start moving. I want you to watch right here. So, not moving. Moving. One more time. The elevator here is not moving. And then it moves. That's all you need to know. Based on the information given in the video, what can you say about the motion of the elevator? Really, you can answer that question with the appropriate explanation in like 2 or 3 sentences. So I'd like you to either type or write down on a piece of paper and take a picture of your explanation and upload it to Google Classroom. And that is your classwork for today. And with that, that is it for the video today. So I look forward to seeing your answers on Google Classroom. And there were some problems uploaded for our homework tonight. There was a solution sheet that was posted today as well. The problems for tonight are the last batch of problems before the graphing test. And the homework tonight is really worksheets from the AP Physics workbook, all about making motion graphs. All right, everybody. Take care.